So we have seen the Newton's approach and energy approach to find the equations of motion or the wave equation for a continuous string. So now we'll look at a question. So that is, we need to write the equations of motion with lumped element. That means that this is the string given rho a t. The t is the tension in it. Rho is the linear density. A is the cross sectional area. X length, z direction, and w displacement all are given. But the a new thing is we are having a mass that is a lumped mass attached at that position, and that lumped mass has a spring attached to it at some distance a from the x is equal to 0 or origin. So the new thing will be we have p of t force coming from that spring to the mass, and the opposite force of p will be applied on the spring by the mass. So this is the equation we'll have right now. So earlier it was going to be equal to 0 because there were no external other force, but right now we have external other force, so we are taking that into account. And the force, this equation was coming from the force balance in z direction, so that the force in z direction is taken into account, and the other force will be this is the equation for this spring, and we are not, so the mass is over here, that the point mass, and the external force is p of t. So since w is the transverse displacement, we are using x, we are using w with instead of x. So that's all we have. Now we are going to define a new function delta. Delta x minus a will be equal to 1 when x is equal to a, and it will be equal to 0 when x is not equal to a. So we are just defining this function. So, and delta is not a displacement, that is just a function f. X minus a is a function. When x is a, it is going to be 1. So it is just a convenience for us. So we are going to make some changes and write this equation of motion for the spring in new terms with respect to delta incorporated. So we can take that. So this is 1, this is going to be 1, and so we are effectively not changing anything. This value is going to be 1 because it is, the spring is exactly at the distance a, and x is equal to a means this is value is going to be 1. So now let's come to the combining equations. So we'll combine those two equations, that is the equation for the string and equation for that spring and mass. We have combined the equations, and the p term goes to 0 because over here we have minus p, here we have plus p. So that's we have. And now we will solve the second order partial equation. This is the partial equation in second order with x and with t. So we can solve that by separation of variables. So over here I am again going to just skip through it because this is not going to ask some anywhere. We just the main point is you must remember that how can we solve a second order partial differential equation. One of the method will be by separation of variable, where we'll separately write all the variables. So one of the function will be w, which is function of x, other function is t, which is a function of t. So we have separated the two functions which are independent of time and space now respectively. And now this is similar to normal mode oscillation response, where x was equal to x cos t. The x was constant earlier, but right now it is going to be a function of x, and the second part is the function of time. So over here we have a function of time. So the w of x will give us the normal modes, that is the function which are going to give me the mode shapes, and t of t is the change in system with time. So I have substituted this w of x comma t in the original equation, and again by separating spatial and temporal terms from this equation, I have separated the temporal spatial terms here, temporal terms here, and I have lambda over here minus omega square. I am writing that is just my wish. The constant is going to be the eigenvalues. Eigenvalues are omega square, that is the square of the natural frequency. I'm using minus eigenvalue or minus omega square right now. So that's a constant. Omega square is also going to be constant, minus omega square is also going to be constant. So I've just taken that, I've separated the terms. So I'm going to use the spatial coordinate and omega square minus omega square. I'm going to use the temporal terms and the omega square. So I'll get two equations. I can again solve these equations, and what I'll get is, so I'll get the same thing which we have got earlier. So let me just again show you that. So we'll again get these same things, which are the time and displacement separately in terms of cos and sine, and the four constants A, B, C, D. We can get the constants from boundary conditions and initial conditions, and as per those, we'll get the response. So we will end over here. We have solved the question. We have made the equations of motion clear from there. Okay, thank you.